Hi, my name is Bahadur Ahmedov. In this video lecture, we are going to discuss about the limit laws, which are very useful in calculating the limits. So, well, first of all, define what is a limit. So when we write down the limit of the function f of x, when x approaches a is equal to L, means that the value of the function f of x gets closer to L as we get closer to A for the x. So as we are going to get closer and closer to the A for the x, the value of the f of x gets closer and closer to the L. So this is what does it mean, roughly, approximately, the limits. And of course, we need to define what does it mean, this word closer. I put this in the codes because it is not so clear for us what does it mean exactly. What does it mean, the close enough? And we are going to discuss about this in our next video lectures. But today we're going to discuss about the 5 limit laws. They are the following. The first limit laws so first of all, I need to mention that the limits are very flexible in terms of the operations with them. So let's say you've got the limit of the function f of x and the limit of the function g of x. They exist when x goes to a, right? Then if you would like to evaluate the limit of the sum of these two functions, so if you would like to find the limit of the f of x plus the g of x when x approaches the a, so when x approaches the a, it appears you can simply open the bracket. So you can write this down. There's a limit of the f of x plus the limit of the g of x separately when x goes to the a and x goes to the a. So it works for the subtraction as well. So it works for the plus and minus. So at the same time, so there is a second rule of the limits. So if you know the limit f of x when x goes to the a, and if you would like to find the limit of the function where this is going to be multiplied to some constant, so use a constant, so you can take out this constant out of the limit. So it is going to be the constant times the limit of the f of x when x goes to the a, where c is going to be some constant. So let's do an example to illustrate how these two rules can be used. For example, if you would be interested to figure out the limit of the function f of x plus 5g of x, and let's assume that you are already given the limits of these two functions. So let's say the limit of the f of x is equal to the 1 when x approaches to the minus 2, and the limit of the g of x is equal to the minus 1 as x goes to the minus 2, and I would like to know what is the limit of this function, f of x plus 5g of x. So it appears these two laws of the limits allows us to write down this big limit as the small is split this into the small parts. That is going to be the limit of f of x when x goes to the minus 2, right? So we can do this using the first law plus 5 plus the limit of 5g of x when x goes to the minus 2. So at the same time, we can write down this. So I'm just going to copy this at this stage. So using the second law, we can take out this 5 out of the brackets. It is going to be the limit of the g of x when x goes to the minus 2. So since we know that the limit of the f of x is equal to the 1 and the limit of the g of x is equal to the minus 1, I'm just going to directly substitute them in order to get the answer, which is equal to the minus 4. Well, there are two more important laws, the limit laws. The number 3 is going to be, so it appears if you know the limit of the f of x and g of x together, then you can figure out what is going to be the limit of their multiplication. When x approaches some a, it is going to be simply, it appears, the multiplication of the limit of the functions separately. So which is very cool feature of the limits. So if you would like to figure out the limit of the multiplication of the functions, just split them out. So in the number 4, it appears it works for the quotient as well. So the limit of the f of x divided to the g of x when x approaches the a is going to be the limit of the f of x divided to the limit of g of x when x approaches the a, and of course when g of x is not equal to the 0, or the limit of the g of x, is not equal to the 0. So let's do another problem in order to illustrate these two properties. So well, I think we can try to do this problem. So let's do another example. So we are going to evaluate the limit of the function, like so what kind of function we had? Oh, let's do this like this. So 2x plus the 3 divided to 5 minus 3x. Okay, so let's evaluate this limit when x approaches the 1. So just using the property number 4, I'm just going to write this down as the limit of the 2x plus 3 when x goes to the 1 divided to the limit of 5 minus 3x when x goes to the 1, and that is going to be, so then by just using the first and second laws, I can write this down as a 2 times the limit of the x when x goes to the 1 plus the 3 divided to the 5 minus 3 times the limit of the x when x goes to the 1. So when x goes to the 1, the limit of the x is simply going to be 1, right? It is going to be 2 times the 1 plus the 3 divided to the 5 minus 3 times the 1, and that's going to be 5 over 2, right? Okay, so or like a 2.5. Okay, so this is how the third and fourth laws also work. But look at this example. So here, at this example, what we could do from the beginning is, but we could just directly substitute the x to be equal to the 1 here, and we would simply get 2.5 instead of applying all of these rules, right? So understanding these rules are very important, okay? But you don't need to write them down always. So it appears we can substitute the values of this limit when x goes to the 1 directly if your functions are polynomials or the rational functions. So this is called like a direct substitution. So the direct substitution property, which basically tells us that, hey, if your function f is a polynomial or a rational function, then the limit of the f of x when x approaches the a is simply going to be f of a. Okay, so it works for the polynomials. So let's do an example. So let's say I would like to find the limit of the x in the square minus 1 when x approaches the 1. Okay, so since this is a polynomial, right, I can directly substitute the x to be equal to 1 to here. It's going to be 1 in the square minus 1. It is going to be equal to the 0. Or we can try to do this for another type of the functions, in other polynomials. Example. So let's find the limit of 2x in the cube plus 3x minus 5 when x approaches the 2. So since this is a polynomial, I can again directly substitute the x with the 2. In general, it is not allowed to do this, but for the polynomials, it appears we can do this. It is going to be 2 times to the 8 plus 3 times to the 2 minus 5. It is going to be 16 plus 6 minus 5, which is going to be equal to the 17. Well, it appears direct substitution not always are going to give us the answers. Even though we directly substitute, sometimes we won't be able to get the answers. So, for example, so this is very important example conceptually. when we need to evaluate the limit of x in the square minus 1 divided to the x minus 1 when x approaches the 1. So this limit we discussed in our previous video lectures when we discussed about the tangent lines to the parabola. Was the equation y is equal to the x in the square. And the problem with the direct substitution is that if you directly substitute this, it is going to be equal to the 1 in the square minus 1 divided to the 1 minus 1, which is going to lead to you to the like a 0 over the 0, okay, which is not defined. So what we can do is actually, so we can simplify this out. So instead of just directly substituting x to be equal to the 1, we can simplify this expression first of all. So I can write down x in the square minus 1 as the x minus 1 times the x plus 1 divided to the x minus 1, right? Then we can cancel out these two things. Then what we are going to have is the limit of x goes to the 1 of the x plus 1, which is going to be equal to the 2. And that's the true limit. And we know this from the previous example as well. So if you remember, so we needed to find the tangent line. So the tangent line to the curve y is equal to the x in a square at the point a of 1 and 1. And the slope of this tangent line m is going to be equal to the limit of x in the square minus 1 divided to the x minus 1 when x goes to the 1, and that's equal to the 2. Okay, so the direct substitution always works, so we need to do the simplifications before we directly substitute the terms. So let's do another example on this matter. So another example would be so defining the limit of 3 plus h in the square minus 9 divided to the h when h goes to the 0. So you can see here again, so if you directly substitute this, it is going to be 3 in the square minus 9 divided to the 0, which leads to the 0 over 0 again. So what we have to do, first of all, we need to simplify the terms. So by just opening the brackets, we can write this down as a limit of the h goes to 0. Let's open the brackets. It's going to be 9 plus 6h plus h in the square minus 9 divided to the h. Then this 9 and 9 are going to be cancelled out, okay? And we can write this down as a limit of. So we can take out the h's from the brackets for these two terms. It is going to be, so if I take out the h, it is going to be 6 plus h here, divided to the h. So we can divide this h, and what we are going to have is the limit of the 6 plus h. When h goes to the 0, it is going to be equal to the 6. So you see, so the direct substitution would give you 0 over 0, which basically means nothing, right? So it doesn't define it. But if you do the simplifications, you're going to get a pretty finite answer. So, and this is going to be the key. So direct substitution works when you've got the polynomials, but usually for the rational functions, try to simplify your answers as much as possible before you directly substitute the value of the x. So this is the 4 properties of the limit. So in our next video lectures, we're going to discuss about the other properties of the limits and their examples. Thank you very much for your attention. I hope that this was helpful for you.